Oh, we'll have to cut it off there. Such a beautiful theme. All right. Good morning, everybody. How you doing? Are you prepared for fun and excitement today? Because today's going to be one of those awesome days. Okay. I have planned it out. There's always going to be at least one super awesome day every week, and this week this is it. Because we get to go outside today. Okay. Those poor suckers at home that have to watch the video afterwards. Well, you can go outside from your own house if you want, I guess, and there's no one stopping you, right? So we get that freedom today. Here's what we're going to do. We are going to measure the height of the flagpole. Okay? Now, you might imagine that sounds rather difficult. Is somebody going to have to like climb up there and hold the end of the tape measure at the top of the flagpole? Okay? I hope you're ready. No, that's not what we're going to do. That's ridiculous. That's dangerous. We have the power of trigonometry and geometry on our side. Okay? We have technology. Actually, really, really simple technology. In fact, I went ahead and I built some of these ourselves. I wasn't sure time-wise. Now they're all tangled up. If we would have the time in class for you guys to build your own. So I assembled them myself last night with some materials just from the Dollar Tree, okay? I picked up these file dividers, so a little bit thicker of paper, okay? Give it a little bit of structure to it. Drinking straw, piece of string, and a binder clip for weight, just so that the string, falls down and dangles, okay? This is the technology we will be used. This is the tool that will help us measure the height of the flagpole. Those of you watching at home, I've posted there on the classwork entry for today a link to I think it's WikiHow, okay? Full instructions on how to build one yourself, okay? So have no fear. And if you guys, I only made enough for the class set for all periods today, so you don't get to take this home with you. I'm sorry. If you want to make your own so you can have it at home to measure all kinds of other things around, you can do that. Follow the instructions there, okay? But here's where that helps us. Because one measurement is really easy to do. Wherever you stand in relative to the flagpole there, it's very easy to measure this, right? Horizontal distance, how far are you standing from the flagpole? Agreed? That's pretty simple to do. We can all do that. We've got a tape measure here. We can go stand there and see how far you are from the flagpole. And what we're going to do is we're going to use this device to sight in the diagonal distance from your eyeballs to the top of the flagpole, right? And now that is the same distance. Your eyeballs are the same horizontal distance from the flagpole. And then what we can find, what we can calculate then is this height. Let's call that y, okay? The flagpole is perpendicular to the ground, so this is a right triangle. I have x. I just need to find y, right? Y is not the total height of the flagpole, should be noted, okay? Y is flagpole from your eyeballs, okay? So we also need to know how tall you are to get the total height of the pole, right? Just keep that in mind. But the mathy bit is, how do you find the other side of this triangle when I only know one side? I need one more thing, okay? Pythagorean theorem says if you know two sides, we can find the third. I only know one side. Shoot, Pythagorean theorem's no good. What other tool do we have? We don't have full-on trig ratios yet. You'll get there. But what we have right now is special triangles, right? If we can determine this angle here, I'm going to call it theta. That's a Greek letter, right? That angle there. If we can set that angle to one of our special triangle angles, we can very easily determine the other side. Agreed? We've been practicing some of that in the problem set that you guys totally started last night, right? I know how you operate. It's due Friday, so you don't look at it until Thursday night. I know. Okay? You do it to yourselves. All right? It's not a short problem set, guys. Don't wait till Thursday to start it, please. Okay. So if we know the theta, we can find the opposite side here, right? Now, we have two special triangles to deal with, 45, 45, 90, right? And the 30, 60, 90. Which one do you think is going to be the easiest to use? They both have a unique relationship between the two legs of the triangle. So let's do this. We'll be multicolored. Okay. If, right, theta is 45 degrees, okay, then our triangle, hang on. Yeah, there we go. Right? Is a 45, 45, 90 triangle. That's our special triangle, right? We just need to measure that one angle. And then these side lengths, this is x. The hypotenuse is x times the square root of 2. And that other leg is what? What? Why? In terms of x. If we know this length, this is that times root 2. Why don't we do an example? Pick a number, right? Let's not use x. Say it's 5. This is 5 root 2. What's the other leg of the 45, 45 triangle? You should know this. It's an isosceles right triangle. What do you know about an isosceles triangle? It's what? No, by definition, what's true about the sides of an isosceles triangle? Are they all different? No? Are some of them the same? Are all of them the same? No, that's equilateral, right? Isosceles says how many are the same? 2. I've given you 2 measurements already. Are those 2 measurements the same? Therefore, right? Deduction, right? Process of elimination, that last side has to be one of those 2 numbers I already gave you, yes? Which one should it be? It should be 5, because that's the symmetric side, right? This 5 is across from 45 degrees. This 5 is across from 45 degrees, right? These are the matching legs. The 45, 45, 90 is the isosceles right triangle. It's the most symmetric right triangle we've got. Right? If I was to, cut it in half that way, I would actually create 2 more isosceles right triangles. In fact, that is how I constructed these last night. I took my square paper, I fold it in half, get a 45, 45, 90 right triangle. And then I took those and I sliced them in half to get these, right? So I can take 2 of those. That way I doubled the number. I thought, that's a little bit big. If I cut it smaller, I can have twice as many for the same amount of paper, right? Save on resources. So that's what I did, okay? It's symmetrical, which means it is the absolute easiest, because if we can somehow know for a fact that from where we are standing, it is a 45-degree angle up to the top of the flagpole, and we're standing, I don't know, how far away do you want to stand? Pick a number. 10. Okay, yeah, we'll still use green. If x is 10 feet, what is y? 10 feet. Right? That means if you position yourself such that when you look up at the top of the flagpole, and it's a 45-degree angle, then however far you are from the flagpole, that's how much taller the flagpole is than you. That's pretty handy, right? Pretty good, huh? Now, if you can't get there, right? Say maybe you're in a limited space, like if we're in this room, okay, and I can only get so far away from something, we're limited, and I can't get matching distance. I can't do 45. You'd have to use the other one. So, just for the sake of example, if you had to stand much closer, okay, theta was, we'd use our other special triangle, the 30, 60, 90 triangle. And we'd go theta is 60. So now we have this triangle, right? Here is 60, here is 30, okay? And you measure some distance, you're 5 feet away, okay? That 5 feet is the short distance, okay? So if you can look up, and granted 45 is about, there, 60 is higher up. So you get closer to it. So you're looking more up, 60 degrees up. Then your distance is the short leg of the special triangle. The hypotenuse is the longest leg. It's twice that. It's 10. Do you guys remember what the third leg is? The one across from 60 degrees. The hypotenuse was 5 times 2. This is going to be 5 times what? What's that? 3? Almost. It's related to 3. The square root of 3. Yeah, 5 would be too big. Sorry, 3 would be too big, right? Square root of 3, right? So those of you at home, if the thing you want to measure, right, is like, it's actually going to be 20 feet tall, but you can't stand 20 feet away from it, okay, you have to get closer, you might want to go with a 30, 60, 90 triangle. And then the only difference is, instead of taking the exact same length, you have to take your distance from and multiply by the square root of 3. Just put that in your calculator. One extra step, right? Not too bad, right? If you had to. Okay. Questions so far? All right. Then we got to talk about the device itself. So this is called a clinometer or a clinometer. It measures inclination, clinometer, right? Clinometer. Here's how it works. This is a basic clinometer. It only measures one angle. This only does 45 degrees. Okay? If instead you made it, instead of just a triangle of paper, you used a whole protractor, you could measure any degrees, right? You could stand at a particular spot and measure what the angle is, right? You could pick your spot first, then measure the angle. We're doing it backwards. We're saying, no. We want the easiest possible computation, right? Right? Mathematicians are as lazy as possible. We're going to be that way. So we're going to pick 45 degrees first, and this sets your position. So what you do is you hold this thing up to your eyeball, and you look through the straw, okay? Try not to poke yourself in the eye. Look through the straw at the object you want to measure, okay? If I look at you guys, notice the string is dangling way down here. It's way off the mark. Am I holding this straw at a 45-degree angle to the horizontal? No, right? We know that, well, the triangle should sit like this, right? So I need to look at something up higher, right? Position yourself so that when you look through the straw at whatever you're trying to measure, right there, right? The string dangles, and I marked it parallel. Right there, right? Maybe you have to move. Oh, I need to move closer, or a little further away, such that when I tilt this, it lands on that mark, okay? And that's the spot. And then you can say, oh, right here. From here to the top of the flagpole is 45 degrees. And then you measure your distance from where you're standing to the flagpole. You can calculate y. You measure your height, specifically your eyeball height, right? Because you're measuring the angle from your eyeball. So don't go all the way to the top of your head. If you know your height, you can probably subtract maybe like 3 inches and get that if you already know how tall you are. Otherwise, we can measure you. Okay? Any questions on how this is going to work? All right. Then, any extra time after this computation, right? You'll submit your answer there on Google Classroom, and then extra class time, you can start or continue to work on the problem set, okay? So that'll do. I'm going to wrap up